Okay, I wanted to make this video to explain in a little more detail why the claim that the instantaneous rate of change of a function at a point is equal to the slope of the tangent line at this point. And so what I want to do to illustrate this is to use the problem we used in class, which is problem 7 in chapter 2, section 1. So they gave us some values for distance and time in a table, and I've plotted these points. These are the little red points. And then I've kind of best fit this to a curve. This is the dotted curve right here. It kind of best fits the points. And what I'm going to be interested in is the instantaneous speed at t equal to 1. And so the strategy is we're going to pick points to the right of 1. We're going to look at the average velocity from that point to 1. And then we're going to let these points move towards 1 and see what happens to the average velocities. So this is like the problems you have in the homework where you have these 2 points P and Q. And P is a fixed point. In this case, this is the point at t equal to 1. And Q is the point that's moving towards t. Okay? So here is the tangent line at t equal to 1. And if you use the equation for this curve, I won't go through how I got this. But the slope is basically 1.667. And you could actually just plot this and estimate from a graph, okay? Just like you did in the homework where it asked you to plot the graph and then estimate the slope of the tangent line. Okay, so that's the slope of the tangent line. Now I'm going to consider the secant line that's going to give me the average rate of change between 1 and 5. Okay, so there's the secant line. It's going to give me the average rate of change between 1 and 5. It has a slope of 6.1. Okay, now I'm going to consider the secant line that goes through t equal to 1 and t equal to 4. It goes through the graph at those 2 time points. And so we notice that here the slope is less, and it's getting closer to 1.667. It's still far away, but you can see that the values of the slope are decreasing as the right-hand endpoint moves towards 1. Okay, now let's consider the average velocity between the time interval 1 to 3. And if I compute the slope here, this is the average velocity. It's 4.65. And again, you can see that the values of the slope are decreasing. Whether they're actually approaching 1.667 is hard to tell because they're still far away at this point. And lastly, I'm going to look on the interval 1 to 2, and I'm going to be interested in the average rate of speed, the average speed. And of course, I know that's the slope of the secant line, and I can work that out to be 3.7. And it's rather difficult to draw, but you can convince yourself if you were to draw points much closer that this slope would continually get smaller and smaller and smaller as the right-hand endpoint moved in, and it would approach 1.667. Okay. Now, what you can see, what is pretty clear, and this is what we did with the spaghetti exercise, is you can see that the secant line is morphing into the tangent line. Okay, that should be, I think, pretty clear that as that right-hand endpoint is moving towards 1, that secant line is slowly converging to the tangent line. So here's the logic we want to use here. Okay, so here I want the instantaneous velocity at some point t is equal to, instead of a, I'm going to have 1. And so I'm looking at these intervals where a is going to be the left-hand endpoint. I'm going to make the interval smaller and smaller. And here's what I see. The secant lines converge to the tangent line. I see that from the diagram, which means the slope of the secant line converges to the slope of the tangent line. But I know the slope of the secant line is the average speed. So I know that the average speeds converge to the slope of the tangent line. But we said in class, as that interval gets smaller and smaller, the average speed should converge to the instantaneous speed. So this tells us that the slope of the tangent line must be the instantaneous speed, because the average speed is converging to the slope of the tangent line, and the average speed, we know physically, must converge to the instantaneous speed. And that's the argument. That's the train of thought we want here. All right, I hope this helped. I think this is a good video to kind of think about And if you have any questions about any part of it, please let me know. All right, thank you.